All right, sorry for the delay. I forgot my iPad. It was in my office, so I went back and come back. Okay, so all right. So how was yesterday's midterm? All right. Um, okay, so your facial expression reminds me of an episode of South Park，知道吗？南方公园啊。OK，现场有我们外籍生在吗？那我来讲个笑话，因为我刚刚临时想到，有一次我看那个南方公园有一个那个 episode，他在讲说，你知道南方公园那个 Kenny 有没有？知道我在讲谁吗？南方公园的 Kenny 他是怎么样的一个情况？Kenny 就是有一个叫 Kenny 的 South Park。How many of you know South Park？South Park， 南方四剑客啊，里面有个角色 Kenny 嘛，哎，Kenny 就每一集都会死啊。反正有一个叫 Kenny 的每一集都会死啊。那这有一个很深的寓意在里面呢、大家知道吗？因为就代表说社会上有些人他死了也没人会 care。然后他复活也没人会 care， 反正他就有一个 Kenny， 真的你就去看了 ，Kenny 每一集都会死啊，通常就莫名其妙就死了，车祸之类的啊，然后就其他人就继续演了啊。但是有一集 Kenny 一直到最后才死啊，就是专门给他的啊。那个 Kenny 那集呢，他那集大家发现他很会唱歌这样，但是他家非常穷啊，不可能给他去上音乐学校啊。那所以他就不知道为什么就被他妈妈就发觉东欧那个有个国家叫罗马尼亚，那边的学校比较便宜啊，所以就把 Kenny 送去罗马尼亚去上声乐啊。然后那个就 Kenny 果然就很有才华，在罗马尼亚就爆红这样，大家发现有个天才的 Kenny 美国来的 Kenny 很会唱歌这样啊。后来那个反正就是。他妈妈他们家很穷啊，所以他就接受罗马尼亚电台专访啊，说你喜不喜欢罗马尼亚这样？罗马尼亚是很穷的国家，然后那个 Kenny 他妈妈就说 ，Kenny 妈就说，我们超喜欢罗马尼亚 ，We love Romania here because everybody is as poor as we are 这边所有人都跟我一样穷，所以我觉得我超爱这里啊。那如果大家都觉得考不好没有关系哦 ，Please love DSP because everybody is as poor as I am 好吧，如果大家都均平也蛮不错的好，想到这个也很深的寓言。结果那集大家可以去看了，Kenny 到最后才死啊，死因我就不破梗，还是死了不管你说还是死，但是死因蛮 sad 的那集好。Okay, so yeah, back to DSP. All right, so we were our topic was structures, 结构 structures. Okay, so we will be drawing a lot of flow diagrams. Flow diagrams. Starting last week, this week, and into next week. Okay, 会画很多的 flow diagrams. All right, so all about structures, how we process signal by branches and arrows and node, summation, feedback, and so on, right? So a bit of recap from last time. We introduced what we call direct forms. Direct form number 1, direct form number 2. Now, what are they? So direct form number 1 is this kind of structure, okay? So we will start by discussing second-order systems. Second-order systems may have up to typically 1 0, maybe 2 zeros, okay? And 2 poles. So an example that we talked about last time was this system function. And so you realize that it's been too many colors on this slide, but I suggest that you could just memorize this structure. It's pretty easy to analyze. Okay? It's not that hard to follow. So with these coefficients, here you have 1.5 right here, and we have 1.5 right there. Minus 0.9, minus 0.9. And please pay attention to the sign, 正负号, plus or minus. Okay. So for feedback, there is a change of sign in the coefficients. But for feed-forward, there's a factor of 2, which corresponds to this term in the system function. Okay? So when we put everything together, you can be sure about that the system function equals to, when we divide y of z being the z transform of the output, when we divide the z transform of the output with the z transform of the input, yz divided by xz equals to the ratio of two polynomials, right? A rational function of z inverse, and all the coefficients show up in the flow chart, in the flow, okay? So just rather, I would just encourage you to simply memorize this structure. It's not that hard to analyze, okay? Direct from number 1 with summation right here, okay? But soon people realize that we can, because of commutativity, 这个字我把它写下来 commutativity 可交换性 commutativity 可交换性 commutable because the linear time invariant systems are commutable in the sense that their impulse responses convolve with one after another. Okay, and convolution, as we know, is commutable. It's a commutable operation. 是一个可交换的运算元commutable operation. So therefore, even when now we are drawing a system diagram, we can change the order of our subsystems, change their orders, change the order they show up on the flow. Okay, so we can as well arrange the signal to go through this system first, then through this system. We can change the order they appear in the flow. And the result will be direct form number 2. Okay? The result is, if you just take a close look, just mentally copy this system to your left, that's the system. And you can mentally copy this system and put it to the right right here. And then soon we realize that by this change of order, we can also arrange the delay line in the middle. We have a line of delay. Z inverse, this denotes one sample of delay, right? Now we can arrange the delay in the middle and by changing the order of subsystems. So now we have the delay in the middle and feedback to the left, feed forward to the right. The organization is like that. So simply, please take a mental picture of this, and we understand it that this is our direct form of type 2, direct form 2. And they represent the same system. The system function is still the same, with the same coefficients, everything, all the coefficients are the same. So now we have direct form number 1 and direct form number 2. And today we will continue to talk about cascade versus parallel. Okay, cascade versus parallel. And now we have in this flow, taking this flow as an example, right? And we claim that this is an implementation of a sixth order system with 3 blocks, 3 second-order subsystems like that, and they are put in cascade. 串接起来, they're put in cascade. And each subsystem is a second-order system with now direct form 2, right? Delay line in the middle, feedback to the left, feed forward to the right. And we have also introduced a notation that whenever we see 2 branches flowing into the same node, that means summation. Okay, that means summation right there. And if we have a branch out situation, then that's simply branching out. Okay, and we have put all the coefficients right next to the arrow to indicate multiplication by that number, scaling by that number. So it's pretty easy way, branch in, branch out. And we have 3 subsystems, and this is a 6th order system, an implementation of a 6th order system into 3 blocks of second order systems. And what's going on right here? Okay, what's going on right here? So this is, first of all, this is of course an IIR system, okay, with feedback. with feedback here, summation here. So you imagine that this feedback will keep looping like that. So the impulse response, when we send an impulse right here, a delta function right here, the response will just keep feeding back and sum with the previous results. Okay, same thing here, feedback, feedback. So the impulse response is definitely infinite impulse response, and this is an IRR system. And I share with you that this is often this will happen when we, for example, design a Butterworth filter, a Butterworth sixth order Butterworth filter. Okay, so to put things into context. 不在什么样情境会遇到? So if we ask in what context will we encounter this situation of having a sixth order IR system? My answer is, for example, if we design a sixth order Butterworth filter, yeah. So if we design sixth order Butterworth filter, what do you remember? What do we remember? Sixth order Butterworth filter. Maybe let me use a space up there. I believe I have a blank space. Yeah. So context. So let's put things into context. Okay. Context. Sixth order. Sixth order, let's recall how do we design a sixth order Butterworth filter, Butterworth low-pass filter. Is that in this context, we start with the S domain, right? We start with the S domain, and we draw a circle. It's a circle with a radius of big omega cutoff, right? And we cut pizza, right? Let's just try to recall. Now we cut pizza, and then we may introduce 3 poles right here and their conjugate. We have a total of 6 poles in conjugate locations. In 3 pairs of conjugate poles in the S domain, right? This is the context of using an analog prototype first, and we know that we need to cut pizza to the left-hand side. And then what happened? What kind of transform do we apply? By now, I assume that we all remember we apply bilinear transformation, right? We apply bilinear transformation. So now we say our design h of z is defined as h continuous time of s of z, where s of z, does anyone remember, s of z is what? 2 over td, 1 minus z inverse, is that right? Yeah, okay, good. Yeah, thank you. Yeah, but details is, there's a mapping. There's a mapping, and so the result, the outcome, we have a filter in whose poles can be found on the z-plane, right? On the z-plane. And since we know that the left-hand side of S-plane is mapped to the inside of a unit circle in the z-domain, so we can be sure that the resulting this, great. This is stupid. Yeah. Okay. Now we can be sure that the resulting poles will be somewhere after transformation. They will occur somewhere in the inside the unit circle. Right? Inside the unit circle. Let me just my drawing may not be correct, but inside the unit circle we will have 6 poles. Okay. Also in conjugate locations. And also we have, if you work out the detail, you'll find that we create a 6th order 0 at exactly z equals to -1. Do we remember that? Does everybody remember that? Let me put the number 6 right here to emphasize this is a 6th order system. So we have something, now the resulting design can be written as, I believe, it can be written that 1 plus z inverse to the 6th order. And the bottom, a of z, in a of z we have, in general, it can be decomposed into z minus z1, z, I better not put it this way. Let me just stick with our convention. Okay, we can factorize. 我们可以把它因式分解啊。We can factorize. We can factorize a of z into the product of 6 terms, 1 minus, let's say, 6 different poles from j from 1 to 6, zj, z inverse. Okay? So basically, we have 6 poles here denoted as z1, blah, 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 to z6. Okay? And there are 6 of them, 6 poles in the z domain. And there may be a constant somewhere, so let me put a big constant k right here. Yeah, a scaling factor. So these are like some details you can all figure out either by calculation or by computer. Okay, yeah. So this is a kind of context. In this context, you are designing the FIR low-pass filter indeed, and indeed the resulting system function has 6 zeros and 6 poles. It's a 6th-order IR system. Okay, yeah. So of course, in the last lecture, we argued that now A of z, really A of z, can also be written as 1 minus summation a1 ak z minus k from 1 to 6. Okay. Oh, yeah. And B of z is simply k times 1 plus z inverse to the 6th power in this example. And it can be written as b0 plus b1 z inverse plus blah, 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 plus b6 z to the minus 6th power, right? So in the previous lecture, now we can have a direct form type 2, if you will. Okay? If you want to, we can just draw a system diagram in the second kind of direct form, right, with delays in the middle. So let's try that. Okay? This is a 6th-order system, so we have delay line in the middle, the inverse, 6 of them. The inverse, the inverse, the inverse, 6 of them, the inverse, the inverse. Seriously, that's what we mean. Okay? One choice of implementing this 6th-order system directly is just to put everything together into one system in direct form, okay? In some direct form. And we know that branching out would be feed forward to the right. Okay, so feed forward, feed forward, feed forward, feed forward, feed forward, feed forward to the right, and feed forward to the right. 1, 2, 3, 4, 5, 6. Okay, now so this is B0, B1, and so on, all the way to B6. And then we would sum up, like that. Okay, sum up, and sum up. Seriously, that's what we will be doing. And the other part, the feedback part would involve going backward with a coefficient. And just pay attention to the plus and minus sign. Here I have introduced a change of sign right here. So I can, if I get this correct, I think I can just directly say A1 right here. Okay, A1 feedback, A2 to the left, and so on, and so on, and so on. The last term is A6. And then we will sum up, and so on, sum up. Whenever two branches meet at a node, we sum up. Okay, and in the end, that's branching in, that's x of n to our left. And with feedback, now it's summing, and finally, we can be sure that the output y of n, and this is an implementation. This will be an implementation of our Butterworth filter. Yeah, so that's the entire process. So you can, seriously, we can just implement our filter like that. Yeah, and I believe this is a bit closer to hardware design, even though I'm not an expert in hardware, digital hardware. So you can imagine that this is a bit closer to your, let's say, FPGA, VLSI, whatever implementation. Okay, if you one day you are to develop a digital filter like by producing a piece of hardware, you can do this in principle. But now, today, we are going to suggest a few alternatives. Okay, we're going to suggest that maybe we want to. So today, outline, we are going to suggest that maybe we want to factorize. We want to organize this. Maybe we want to organize this expression by breaking it by factorizing them into 3 subsystems in cascade, and each of the subsystems will be a second-order system. Okay, so we're going to suggest that we might want to just 3 of second-order systems in cascade. Actually, it could be in cascade or in parallel. Or in parallel. Okay, so what does that mean? In cascade means that we are going to let me just draw a quick. You know what I mean. This is a direct form of form number 2, and another one like that with all the arrow pointing in the correct directions. You'll figure out the detail. So in cascade meaning that we can always attempt to reconsider our architecture and just transform this kind of implementation into subsystems of second order. So subsystems of second order filters. And just by choosing the coefficients wisely, we can make them equivalent. Okay, we can make them equivalent. It's doable. Or we can even put them into cascade systems. No, not cascade, in parallel. We can decompose the system in parallel form, like that, with all the arrows pointing to the correct direction, and you figure out the detail. Just let you figure out the detail. It's possible to also transform our system into parallel branches. Instead of cascade, we can also create parallel branches. In fact, we may also need a constant term, okay? Constant term of C0 somewhere, okay? But then we can then sum them. So here I'm emphasizing that when all these branches just meet with one another, they sum up, okay, somewhere. And it turns out that it's also possible to design an equivalent system that will produce the same system function, same I/O relation, same input-output relation, and this is doable, okay, either in cascade or in parallel. So the questions are, okay? So the questions are how exactly to find the equivalent systems, okay? How do we determine the coefficients, right? So we need to touch the details. First question is how do we find out all the coefficients in all the details? All these branches will need to specify exactly what coefficients put in right here. All the coefficients need to be figured out, right? So that's the first question. But the second question is why bother, right? There must be something in here that people don't feel comfortable with. 可能它有什么样的缺陷啊？ There must be some drawbacks or risk in this implementation which made us think that maybe we should first talk about decomposition into subsystems. Okay, so to answer the second question first, okay, let me just briefly tell you the reason for cascade or parallel implementation is because we can more easily control the pole locations after quantizing the coefficients. Okay, the problem is coefficient quantization. Coefficient quantizations. Okay, the big issue here really what motivates us to even consider this different ways of implementation. The key issue really is coefficient quantization. Coefficient quantization. So hopefully we'll show that when we quantize the coefficients, in this kind of implementation, we have a risk of making the system unstable. Okay? It's possible that after coefficient quantization, in this kind of implementation, some of the poles might just accidentally, 不小心的, accidentally be put outside the unit circle, and that's something that we don't want. Okay? Even though we begin with a nice design with all the poles inside the unit circle. But if some of them are close to the boundary, are close to the unit circle, then it could happen that after quantizing the coefficients, the poles can move outside. Okay? And that's something that we hate. Okay? Yeah. So therefore, this is that's the issue. That's why we may need to consider cascade coefficient, and we'll show that in this 这种田字形, in this second order system, we can always be sure exactly where the poles are going to be located even after coefficient quantization, and we can ensure that they are always inside the unit circle. Okay? That's why we need to consider cascade or parallel structures. Okay? So far so good? Okay. So now, a bit of detail. How do we transform our sixth order system into a cascade of 3 second order subsystems? How do we do that? How do we do that? So the key is to realize that when we have 6 poles, when we say h of z is bz divided by AZ, which in turn is equal to summation BK Z minus K, and we here K goes from 0 to 6, divided by summation, I should say 1 minus summation K equals to from 1 to 6, AK Z inverse K. Okay, the first thing you should do is to perform, to find the roots. Okay, to find the roots. So on top we have B0 that can be put outside, and we have a product. Okay, so let's denote make our notation clearer. So we have 6 poles, Q located at Q1 to Q6. In this example, K goes from 1 to 6. Okay, and at the bottom we will have a product of 6 poles. Product of 6 terms that corresponding to 1 minus pole location PK Z inverse. Okay, so let's say our notation is PK, P for the pole, Q for the zeros. And you can always do that because any 6th order polynomial has 6 roots, right? Any 6th order polynomial has 6 roots. 有6个根嘛，六次方程式有6个根啊。And further, we know that all the coefficients here are going to be real. These are real coefficients. So B, K, and AK are real. Since they are all real numbers, we know that their roots are going to be located either the roots are either going to be real or they are what? They're either real or they occur in conjugate pairs, right? 就是 polynomial, right? If all the coefficients are real, so we know that their roots are either real, either 实根或者复数根或复数根, either real roots or complex conjugate roots. So therefore, in this implementation, I suggest that we are going to organize H of Z. So H of Z, after certain organization, we are going to assume without loss of generality. Okay, without loss of generality, this factor B0 still come out right here, And then we are going to suggest that we just put conjugate pairs of poles into the same subsystem, okay? So in each subsystem, we are going to assume that, let's say, 1 minus P1Z inverse without loss of generality. We are going to assume that P1 and P2 are complex conjugate. We're going to assume this, okay? And in the pole, in the most general sense, we are going to be sure that Q1 and Q2, okay? The zeros is not that important, so then we can say Q1 either is a complex conjugate of Q2 or Q1 and Q2 are real. It's also possible. Sometimes we need that. Yeah. You can be sure that without loss of generality, at least in our example, we have 6 complex complex roots and some real roots for the zeros. Yeah. So similarly, 1 minus P3, no, 1 minus P3 Z inverse 1 minus P4 Z inverse, where on top we can have Q. You have some flexibility to rearrange the order so that Q1 and Q3 and Q4 are complex conjugate or they are simply real. And more importantly, we can ensure that P3 and P4 are complex conjugate. Okay, and you have the same thing, but with 5 and 6. Okay, same thing. You put in just right here with number 5 and number 6 being complex conjugate. I'm running out of space. So let me just write right here. So P3 is equal to P4 conjugate and so on. P5 is equal to P6 conjugate. We can just, without loss of generality, rearrange the order of all the poles. Rearrange the number of the what? How do I say? The index. Yeah, not the number. Rearrange the index of the poles. 那个它的是第几个啊？ Rearrange the index of poles so that 1 and 2, number 1 and number 2 are complex conjugate, number 3 and number 4 are complex conjugates, and number 5 and number 6 are complex conjugate. You can always do that. And then the rest is easy. Then just your insight should be correct. Okay, so now we can just put this here, and put this here, and put the third system right here. Now you can just assign them like that. Yeah. So now each of them is a second order system with feedback, and now we can expand the denominator and numerator. Okay, 把分子跟分母啊. We can expand the denominator and numerator again to become this form. Should I write it down? So we can always expand. So for the first subsystem in particular, for the first subsystem, for the first subsystem in particular, expand them. Expand its numerator 分子 and the denominator. Expand them. So we have the first subsystem and denote it as the first subsystem. H1 of z now equals to, we know you can always expand them. Okay, and the result could be 1 plus B11 z inverse plus B21 z to the minus square. 1 minus A11 z inverse plus, not plus, minus. Okay, so a lot of details about the signs. We want to make sure they're all correct. A21Z inverse. Okay, you can always expand them and just denote your coefficients carefully right there. And then they will show up right here, like that. Yeah. They show up right there. Okay. Any comment? Yeah. Is it? Can you understand this? Ah. 会不会有点太小啊 Can you understand this? Just one each expression right here corresponds to each subsystem. Okay, it's pretty straightforward. Second order system. You can always expand the numerator and denominator. 把它展开就是 expand 就是把expand both parts AZ and BZ, and they will tell you what coefficients to put there in the right places. Okay, and do the same thing for the second factor. Put them, expand the top and bottom, and put them in, just create the correct coefficients. And same thing here for the third system. Create them, put them the corresponding coefficients right there. Yeah. So I just want to just hard to translate. 一个萝卜一个坑 Okay. Just put things in the right places. Yeah. You'll be able to do this. With perhaps a kind of flexibility. Okay. There is a little bit of flexibility of in here. So if you just pay attention, 一个萝卜一个坑 also just put everything in the right places and do the things right, do things right. Do the right things, do things right. Okay. Do the right things, do things right. I like the phrase, 柯文哲. I'm not a fan of him, but I was. He's the only person I donated, the only politician I've ever donated my money. Back in 2000, which year? When he was running the first time for the mayor. I was young and stupid, but no. Oh, no, I was passionate. Do the right things, do things right, okay? It's not that hard. But there's one tiny detail I want to point out, okay? One tiny detail I want to point out is the direct path, okay? Please pay attention to this direct path right here. There's the direct path that goes all the way, fast track, right? No delay in the middle, okay? What does that correspond to? So in this plot, you look at the direct path, you found that the path will just go through the product of three factors, three scaling factors right here. Now, namely B01, B02, B03. So let me just be sure that there is a flexibility right here. Just note that we should have B01 times B02, the product of three of them should equal to B0 right there. Okay, so there's a bit of a flexibility in your design. You can decide what scaling factor to put there. Okay, might be important in practice. You don't want things to suddenly go too big. So there's a tiny bit of flexibility right there for you to assign. But in the end, as long as you ensure that the product of the three of them equals to B0 right here, you'll be fine. Okay, you're going to be fine. So this is a kind of a tiny detail where we have a bit of flexibility. 有点弹性 We have a little bit of a flexibility right here in our design. But otherwise, just put things in the right places. So this is not hard. And the context, for example, is when we design a sixth order Butterworth filter, you might need to consider a cascade structure. Okay? And next, I do want to move on to the parallel structure. Okay? So in this structure, still, we begin with h of z. Same h of z that equals to long division B0 plus B1 z inverse plus and so on to all the way to 6, the last term on top. And we have 1 minus, actually I don't need to put, let me just put 1 minus just to be consistent for this lecture. Plus A6Z, the last term, okay, plus or minus sign. Yeah, there are some details right there. Okay, so for the same system, now let's go through how we transform it into a parallel structure. Okay, so the idea is that we would. This is about different ways of decomposition. It's about 拆解, decomposition. So I'm going to suggest that the first step perhaps would be to pull the factor b1 out so that the leading coefficients on top and at the bottom both are 1. So that both polynomials begin with factor 1. So now we have 1, but then b1 needs to be normalized by dividing with 0. By division by 0, okay? Division by the factor b0 right here. b0 right here has been pulled out to the outside, so now we have to normalize all the coefficients by dividing with b0 and so on and so on. Okay, and the denominator stays the same. Okay, denominator 分母 denominator stays the same. 1 minus a1 the inverse, they stay the same. Same thing right here. Okay. But with that, now we have the situation of a function that looks like this. Okay, let's focus on this function. In this function, it turns out that it is possible to consider one or another, but we can put it in a different form. We can just change it into 0 plus C1 divided by 1 minus P1 the inverse plus C2 divided by 1 minus P2 the inverse, and so on. There is a total of 6 terms. We can do this. We can do this decomposition. We can do this decomposition perhaps using the residue theorem, if you will. Okay? So we know that this is a complex function having singularities, right? So in one way or another, we can always figure out what these coefficients are by using this is pretty standard. It is pretty standard, okay? So perhaps we can, there must be a corresponding MATLAB function that you can use to figure out that how to transform this expression, b of z divided by a of z, into this expression with these factors, okay? And the function, I did my homework, so let me just simply tell you, if you're interested in this procedure, is called partial fractional expansion. Okay, I always forget about this. The key word is partial fractional expansion. 部分分式展开了 if you will, if you translate it directly into Chinese. Partial fractional expansion. Okay, and MATLAB, the corresponding MATLAB function in MATLAB, use residue. There is a function by the name exactly residue. Okay, this is a function you want to check if you ever encounter this the need to create a parallel structure. You will need to perform the expansion, the partial fractional expansion, by changing the format, changing the expression, changing this standard expression into the sum of fractional functions like that. So it's doable. Okay, it's really doable, and it's pretty standard. So note that. So now we can. But now this does not directly correspond to the flow we are seeing right here. The expressions still, we need to organize them a bit, okay, by a similar method, okay? Just without loss of generality again, we can be sure that these 6 poles are in 3 pairs, right? Yeah. We have 3 pairs of complex conjugate poles. So again, just without loss of generality, we can assume, without loss of generality, we can arrange the indexes of the poles so that P1 is P2 conjugate, and so on. Same thing, again. You can always organize them into pairs of complex conjugates. And then after you do that, what do we do? Recombining the conjugate terms, okay? So after we perform this arrangement, we can again recombine them into 3 pairs of 2 terms. Recombining into this just by grouping them into 3 groups, 3 subsystems, and then for each of them, and then after that, just we merge the terms into 1 minus P1 Z inverse, 1 minus P2 Z inverse. With on top, we have C1, 1 minus P2 Z inverse plus, I'm always running out of space. It's bad. C2, 1 minus P1 Z inverse. Okay. Let me blow this up a little bit. I'm not going to do a good job. Yeah. Just combining the 2 terms. You know how to do that. Okay, 通分了. Just you can always combine them. And after this combination, then again we have a second order system. Okay, we have a second order system, and since P1 and P2 are now complex conjugates, since we have this arrangement, all the coefficients after combination, after we combine the 2 terms, all the coefficients are going to be real. Yeah, all the coefficients are going to be real, like that. Be real like that. Be real like that. Okay. But now you notice that the shape is a bit different right here. Okay. So by paying some attention, the shape right here now is not. There's a missing branch right here. We don't have a feed-forward term anymore. That's kind of nice. Okay. That's kind of nice. So in this implementation, note that we don't have this branch. Yeah. And it's because after combining on top, we have a first order. There's only 1 0 for each subsystem. Kind of, that's just the nature of partial fractional expansion. Okay, just because of the nature of this expansion, the resulting subsystems now second order, but with 2 feedback, but only 1 feed forward, or should I say, 2 feed forward, but missing the 3rd one. Okay, and that's nice. That's nicer. Now, can we agree on that? This is kind of nicer than our cascade implementation, where each subblock subsystem has a full 3 forward coefficient, right? We have 3 feed forward coefficient right there, but only 2 right here. So in a sense, this is a better implementation. And we're not even mentioning that things are now in parallel. Okay, so there might be a benefit, an advantage of this design. Okay. But in principle, we can be sure that also there's a constant term right here. So to put everything now goes in parallel, flowing into a constant term and into 3 subsystems. Each of them is a second order term with 1 missing feed forward coefficient. That's nice. Okay, nice here, nice here, nice here. Nothing right here. That's nice. Okay, and everything is in parallel. So in the end, we just sum up all of them, and the output is y then. We can be sure that this is an equivalent implementation of any 6th order system. Okay. Okay. So, so that's it. Okay. So please, yeah. All right. So Next time when we meet, we will talk about FIR. Okay, FIR, and as I promised, there's a benefit, an advantage, a need of transforming our 6th-order system into 3 second-order system, because in second-order system we have better control of pole locations. So we'll emphasize that next time when we meet. Okay, see you next week on Wednesday. Thank you. Yeah. 对，听起来怪怪的啊，怪怪的 expansion， 对，怪怪的，对对对，呀，没关系，你帮我确认一下啊。我写 expansion， 因为我的 note 写 expansion， 好，啊，我们都一直都有录吧？有没有录影片？有，因为我刚刚在网络上没有看到。啊，真的吗？网络上没看到。我在看直播。哦。我跟另外一个同学，我们都没有看到。这样子啊。